In this video, we're going to see a slightly different geometric shape when we do our slices. Let's walk through the scenario where we have a region bounded by the square root of x equals y. That's our classic sideways parabola. And from that, we also have a boundary at y equals 0. That is the height down here. And x equals 4 is that value there. So the region we're talking about is enclosed in this lower right-hand corner on the graph. We are then going to rotate that around the y-axis. And so you can imagine this becoming a circular shape like so. And it's going to have gaps in the middle. So that's going to change the flavor of things. For a moment, imagine what would happen if you did take a slice of this, take a thin slice, cut it horizontally, and then imagine spinning that around the y-axis. What kind of shape would you get? Take a moment to think about that, and then we'll check in. Okay. Well, what we notice is we're going to have this region spun around the axis. And if we spin that, what we're going to get is a hole in the middle, and then everything else. And that is definitely going to give us a new shape. It's going to be a ring, a hole in the middle, and regions outside of that. When we do the volume calculations, all we're going to do is add a thin third dimension to that. But the key thing for our calculations is going to be the area of this cross-section, which is going to be not simply circular, but one circle minus another for the hole in the middle. Now if we look down on that same ring from above, it would look like this shaded region here with the hole missing in the middle. Take a moment to think about what the area of that shape is, the shaded in region, and then we'll come and check in on that. All right, we definitely have pi's involved, so it's not a. The challenge would be deciding between these two things here, and notice those are not equivalent. If we square this, this would give us r out squared minus 2 r in, r out products. So these are not the same. Which one do we want? Well, the easiest way to figure this out is to ignore the hole for a second and recognize that the big circle has area pi r outer squared, pi times r outer squared. And then we are literally subtracting the hole in the middle, which has area pi times r inner squared. Well, that's exactly what this formula here does. It punches a hole in the middle of the larger circle and subtracts the area of that hole. If it helps, you can think of this as the area of the outer circle minus the area of the inner circle. With that formula in mind, we can then go and tackle the problem of finding the volume of slices with this in our particular shape. Here's our region again, and again we're going to take our slices like this, perpendicular to y-axis when we're rotating around the y-axis. We can then see on this diagram the inner radius, and we'll use a different color here for the outer radius. It's always worth exploring to see if one of these is simpler than the other. And you can do that by imagining each individual slice. If you imagine a slice down low, the outer radius is 4. If you imagine a slice up top, this outer radius is 4 again. And so we know immediately that that outer radius is 4 all the time. It's always being defined by this boundary. The inner radius is a little more complicated. It's being defined by the boundary y equals root x, but the r in is the x value on our y equals square root of x. Notice this is a horizontal distance from the axis to a point on a graph. Well, that's what the x-coordinate means. Well, that means we should shuffle this around a little bit, and that's going to give us x equals y squared. So our inner radius, if you tell us what y is, we'll tell you what that radius is. When y is 0, the radius is 0. When y is 2, the radius is 4 for the inner radius. That matches perfectly. We're now ready to find the volume of a slice, which is the volume of a ring with a little thickness to it. And that's going to be our ring area times the thickness. And the thickness, imagine a thin slice like this, is going to be a little increment in y, so we call it delta y. The ring area, we'll do this in stages. Based on our formula on the last page, we take the area of the outer circle minus the area of the inner circle, and then the third dimension is just delta y. And now we can fill in these values. The outer radius is always 4. Careful to get the order right, and we're going to square that. The inner radius is always y squared, and be careful, because we're putting that into a circle, we're also squaring that. And that gives us everything we need to find the volume of a slice. If someone tells us where we're cutting the slice as a function of y, we plug our y value in, we get the inner radius, the outer radius, we can get the volume spinning that around with thickness delta y. Might as well capture the pi's, bring them out front, simplify this a little bit. 16y to the 4 dy. Where do we start? We start slicing at y equals 0. Where do we stop? We stop at the y value 2, noticing that dy is our integration variable. And we're now ready to execute that integral. We'll do that on the next page. Looking at this integral, it's something that we can integrate by inspection. The integral of 16 is 16y if y is our variable. And for the power 4, we add 1 to the power, divide by the new power, and we'll evaluate that at 2 and 0. Keep the pi out front of everything else. We'll have 16 times 2 minus 2 to the 5 over 5. All of that minus 0. And if y is 0, we'll get another 0 there. And that's not too bad. Pi times 32. 2 to the 5 is also 32. And if we do that, that's 32. That'll be 4/5 of 32 with a pi. If you want the numeric value, you get approximately 80.42 cubic units. And that's it. We have worked now successfully with a new kind of shape, one that has rings instead of circles, but the only thing we had to update was our formula for the volume of the slice, taking into account that slightly more complicated shape of one circle minus another. At the end of the day, the integration process looks identical. It's just a little bit of variation in how you build the integral in the first place.